want to cover, just review what we did in lecture last time, which is neural networks. I kind of want to go into a bit more detail as to what they are, the different kinds of architectures that you would use, and how you train them. I want to derive the backpropagation algorithm, and then maybe a little bit as to more recent developments. So the first thing is, I guess I'll just define what an artificial neuron is. Let me find an eraser. Please. So our inputs are just usually some sort of real numbers, set of real numbers coming into the neuron. And we have some output y. And the inputs are usually, the input connections are associated with some sort of weight. Typically denoted by a W. And the node itself, the neuron itself, has some sort of activation function like F. This is typically nonlinear. And this is just what you apply to the weighted input sum. So y would just be equal to F So this is just how you would obtain the output value of this neuron. You just apply the activation function f to the weighted sum of all the inputs for all the connections coming into the neuron. And a neural network is basically just a collection of these somehow wired together to form some sort of directed graph, right, where each node is an artificial neuron of this kind. And they're entirely deterministic, right? So most of our, we've covered lots of different kinds of algorithms and methods in this class. We've covered logistic regression. That's a probabilistic classifier. We've covered naive Bayes is also probabilistic. But we've covered also some deterministic classifiers like SVM, right? Once you have a boundary, you give the label to the point depending on what side of the boundary you're on, and that's completely deterministic. And this is also an example of a deterministic classifier. Once you have an input set of weights, you just follow this formula down for all of the neurons along through the network, and in the output layers, you'll have a deterministic set of outputs. So there's lots of different kinds of architectures for neural networks. And I'll just go over a few of them. So the most popular, I guess, is called the feed-forward. And this is exactly what it sounds like. They're right. You just have some, the neurons are typically thought of as being arranged in layers, but all the connections, move forward in one direction, basically. That's what a feed-forward network is. And one useful way to think about these connections between these layers is as being a giant matrix. So suppose this is probably like a giant matrix W. And so this would be like the number of columns would be the number of neurons in the previous layer. And the number of rows is the number of neurons in the next layer. So then Wij would be, is the connection weight from neuron J in the previous layer going to neuron I in the next layer. And so this is a pretty useful way to look at it because suppose I just have represent all of the values of the neurons in the previous layer with some vector, let's call it x, right? This is x1, x2, xn. Then I can just obtain the values of the neurons in the next layer using a simple matrix multiplication, right? Right. And this is equivalent because if I just take let's see, if I just take the ith value at y, this is just equal to f at f of wx times x. You take the ith element of that vector, which is the same thing as, I'm just expanding the matrix multiplication in here. Right, and that's exactly the same thing as we had there. Any questions on the feed-forward neural network or basic definition so far? Okay. Can I do this? I can't. I have to make this out now. And another kind of architecture of neurons you can have is called convolutional architecture. And this is basically very similar to feed-forward architecture. In fact, it's considered to be a kind of feed-forward architecture where each neuron in the next layer only depends on a local region of neurons in the previous layer. And it's loosely inspired by how neurons are arranged in primary visual cortex in your brain. So you can see that this is part of like a larger network. But each neuron in this layer depends on like a locale of 3 neurons in the previous layer. So you can also have more complex setups, like suppose you have each layers you can think of as a 2D array. And this one could depend on like a small two-dimensional local region from the previous layer. Right. And this one would depend on another different two-dimensional region. And this kind of layer, this kind of architecture turns out to have some pretty big improvements in practice to applications in computer vision. So a lot of the more recent work relies on this kind of convolutional network pretty heavily. There's lots of other kinds as well. Another common one is recurrent. And these are basically neural networks with cycles in the network. So I can have like yeah, or I can have slightly more complex scenarios. And these are useful for like modeling time series, things that, because once you have recurrences in the network, you kind of introduce some time dynamics to the network. So recurrent networks are used for cases where you have time varying data. So.
What's the difference between the first and second? The second architecture, they just like flip it second, first and second.
These two? You'll share, so the question is, which ones do these share neighbors with, right? Like this one, suppose in this two-dimensional case, I use a 3x3 neighborhood, right, of input nodes that feed into every single output node, right? So every output node will be a degree 2 away from a much larger number of nodes in this layer than if I were using this one-dimensional sharing scheme. Because here I'm not sharing with as many connections with as many neurons. So to convert this into this, you have to somehow number these, right? You have to say this is the first one, this is the second one, and so on and so forth. But no matter how you number them, you're going to have some sort of, it's not going to be local anymore. In the sense that the neurons that are being, that are pointing to the same neuron in the output layer, in the second layer, are next to each other, right? You'll have some that are scattered around. Yeah, so that's what I meant by locality. I'm trying to show it explicitly as spatial locality here. If you change this into some sort of one-dimensional form, you'll lose some of that locality.
The region of locality should always lie adjacent in the 1D case, in the 2D case?
I'm sorry, say that again?
I don't know, that's like the 1D case, right? The first one.
Yep.
So is it implicit or is it implicit that when a neuron is influenced by like a group of neurons from the previous layer, they should always be adjacent to each other? Is that a condition?
Yeah, I mean, the convolutional, it's kind of like in the definition of the convolutional network. It has to be local in some sense. You could use different senses of the word local.
I mean like,
right?
So the first one on the second layer is influenced by 3 nodes from the left, right?
Yes.
And so what if these 3 nodes are spread apart? And how does that change things?
Well, I mean, you usually have some sort of coherence in your data. Like, for example, if your data is an image, right? You want to capture space in the image, yeah. So these neurons correspond to distances and locality in the data itself. Like if you also have like a time series, for example, they would correspond to locality in time.
Okay, I guess the data that the data in this neural networks are different. So
Yeah.
they employ the locality.
Yeah, that's why these work well in vision applications, because they take advantage of coherence in vision, in visual images. Okay, any other questions? So here I just presented like the feed-forward layer, convolutional, recurrent. There are lots of other kinds of architectures that are used. Another kind of common one, or there are lots of specialized ones as well. Here's one example of a specialized architecture. It's called like a max layer or a max pooling layer. And each neuron in the output just takes the maximum of the two inputs of all the connections, basically, that it has from the input layer. So it's kind of like pooling the maximums from little local batches in the input layer. And so in general, if you have a neural network that are arranged, they're typically thought of as being arranged in layers. The first layer basically is your input layer. You provide the input values to every neuron in that layer, and then you run the network forward. And the last layer is considered your output layer, where you just, once your network is done running, you basically take the values of your output layer and compare them to, and use that for classification or whatever. And all the layers in between are called the hidden layers or the latent layers. Sometimes they're called nodes instead of layers, like the input nodes, output nodes, hidden nodes. And to train them, you basically use an algorithm called backpropagation, which is equivalent to gradient descent to minimize the squared error of the network. So, and this backpropagation algorithm is also a very, it's basically the textbook algorithm to train neural networks, but also has been very useful and essential in training some of the more recent architectures, like in deep learning approaches. Almost all of them use some kind of backpropagation approach. Let me just get this one. Okay. So, yeah, so let's just derive the algorithm. It was invented in the 60s and is basically the same algorithm we've been using ever since. Yeah, it's basically a textbook training algorithm. So suppose I have a network that I want to train, has a bunch of parameters. The parameters are the connection weights. That's what we want to learn, right? And I have a bunch of training data, training examples. Each training example is basically a pair of vectors, where the first vector is the set of inputs. I can call it X or something. I have a pair of vectors. X is a set of inputs to the neural network. I just set the input neurons and input nodes to the values of X. And then I run the network forward. I get some output values. And I compare them to the values that I have, the labels here, the training labels, Y. Okay. So I'm gonna just establish some notation just to make sure we're clear. So I'm going to denote the layers by a superscript in parentheses. Yep.
So you're talking about label Y here, so what's the neural network has to be supervised with?
This is supervised. Backpropagation is a supervised learning algorithm, yes. There has been some work in unsupervised learning algorithm, but I'm not too aware of that. So I'd have to look into some of the literature. But this is the textbook example, is a supervised learning algorithm. And I'm going to label all of these W superscript 1, where W 1 ij is the connection weight from neuron J to I between the first and second layers. And I do this for L layers. Yeah, and so this set of connection weights is going to be W2. This set of connection weights is going to be W L minus 1. Yeah, so I just feed in each input vector X to these neurons. I run the network forward, and I compare my output Y to this set of output neurons. Okay, and so the objective we want to minimize is the squared error over all our training examples. And just to keep the notation simple, without having to introduce more indices, suppose we only consider one training example, and it's pretty easy to extend it because I'm just going to take the gradient of this objective, and the gradient of a sum is a sum of the gradients. So just for simplicity, let's suppose we have only one training example. And let's call this F. It's a function of all of your connection weights, right? This is our objective. So now let's compute the gradient for a connection weight in this layer right here, in somewhere in the last, between the last layer and the output layer. Okay. So let's compute df dw in layer L minus 1 between neurons I and J. And I just expand that out as a sum. And then I take the derivative using the chain rule Actually, notice that I only care about the connection weight to the ith neuron. So all of the terms that don't consider this the ith neuron are the gradient with respect to those are 0, right? So I basically don't have to. I can drop this sum, and I get right. So I just take the derivative with respect to this. I get 2 times xi to the L times the derivative of xi to the L, which then I can just factor out the 2 and the xi to the L minus yi. So I get and this sum of this weighted sum is just equal to xi to the L, right? That's just by definition of the neural network. And I'm just taking the derivative of that with respect to the connection weight that we're interested in.
Where did the sum come from?
Oh, this is just right. So this is just a convention. When deriving backpropagation, you typically assume the last layer does not go through the activation function. All the layers before it do. And you can easily convert one neural network where the last layer does into one that doesn't, just by adding an extra layer of neurons that just give you the same value as a previous layer, right? So they're equivalent, basically. Does that make sense so far?
Summation over J. So summation over all these layers.
Exactly, the neurons in layer L minus 1. Right, because those are all the neurons that can feed into neuron I.
That influence this particular ith.
That's right.
That xi.
So the ith neuron in layer L is influenced by all the neurons J in layer L minus 1. Make sense? And since we only care about one of the connection weights, these will be 0 for all the others, right? All the neurons J that don't connect to neuron I, right? So our gradient ends up becoming right? So we compute this for every single connection in between the second to last layer and the last layer, the output layer, right? So now let's consider the gradient with respect to the connection weight in the layer before. Yeah, we can do it down here. This is df dw, let's say jk at layer L minus 2. And this is the same as earlier, except we don't drop the first sum. The reason why we don't drop the first sum this time is because if we look at the architecture of the network, all of the neurons can potentially depend on a connection weight 2 layers back, right? Only 2 neurons, or only 1 neuron will depend on that connection weight in the second to last layer, but in the last layer, all neurons could potentially depend on that, right? Because all neurons could get inputs from that 1 neuron in the second to last layer. Does that make sense why I'm keeping the sum? So I just go ahead and take the derivative of this. All right, this is just the chain rule, and I just expanded out XIL by its definition. Right. So now here it only depends on 1 neuron in the layer before, right? The second to last layer it only depends on neuron J. So this sum is going to be, the derivative of this sum is going to be 0 for all of the neurons that are not connected to that particular connection weight that we're considering, right? Wij. And then I can just expand this xj to the L-1 based on its definition. That should be a and here I'm just going to expand xj to the L-1 to its definition, which is just f of a weighted sum of its previous layers of neurons, right? And I check the derivative using the chain rule, and I end up with, I'll try it here. I'm forgetting Wij. And this is just equivalent to xj at L-1 by definition, right? Because it's just the weighted sum of, oh, I'm sorry, it's not exactly equivalent to it because it's taking the activation function. But yeah, anyway. Does it make sense how I got here at least? Yep.
So are you going to do the gradient descent like backwards so that the coefficient is actually the value computed by?
Yeah, exactly. So this is the reason why we're doing it backwards is because it's more efficient to compute, right? Because what is this? This is exactly our gradient from here summed over all of the neurons I, right? Except for the xj L minus 1, but we can store the partial computation of this, right, in some sort of temporary vector or buffer, and then use that to make this much more efficient. We don't have to do a quadratic computation, we can do it linearly, right? So then I just sum this over all the neurons I, and then I multiply it by this term, and that gives me the gradient for for every single connection weight in the second to last layer. Does that make sense? And if you do the same thing for the next layer, which I won't derive completely, but I'll just give you the answer. Let's make this KL, L minus 3 now, is just equal to F prime of that thing times right? So this is now just a sum over j of the previous gradient, right? And we multiply it by this term. That gives me all of the gradients for the next set of connection weights going backwards in the network. Right, so basically what I did was starting with the very first layer, I computed the error, right, the xil minus yi, that's the error. And I'm propagating the errors backwards through the network, multiplying by the weights and these gradient terms, the gradient of the activation functions of the values of the neurons. And depending on, this actually simplifies further if you're using certain kinds of activation functions, like the sigmoid function that has very nice properties. Its gradient has very nice properties. Actually, interestingly, the most expensive computationally part of training and using neural networks is in the computation of the activation function and its gradient. So that's why a lot of the sigmoid function and the hyperbolic tangent function are common ones, because they have these nice properties with its gradient, but they're kind of expensive to compute because they have transcendental functions inside them, like the exp and things like that. So to save computational power, a lot of people will use very simple functions like this. Some of them will use like a piecewise polynomial as an approximation to something smoother. Sometimes you'll use just a step. Right, and these make the computations computationally simpler, although maybe a bit more difficult to derive. But in all of these cases, you use the same algorithm, the same backpropagation algorithm. And here I've shown that backpropagating the errors is equivalent to doing gradient descent. Once you have these gradients for every single weight in your network, you basically just follow the regular recipe for gradient descent, right? You pick some step size and you move along the direction of the gradient with some distance, right? And the step size can be chosen in a wide variety of ways. You choose a fixed step size. Sometimes that doesn't work too well. Sometimes you have to have it decreasing over time. You can choose a step size adaptively. There's some cool new approaches to doing that, like AdaGrad. There are lots of different ways to choose a step size. But beyond this part, doing gradient descent on neural networks is the same thing as backpropagation. And that's the standard algorithm that is used to train neural networks. So I also want to show that this is equivalent to doing MLE under a certain model. You think that that's weird because to do MLE, you need to have a probabilistic model. But the way I presented so far, neural networks are deterministic, right? So to see this, consider the following model. So suppose I have some inputs into my neural network, right? I get some outputs, let's call it f of x, right? And this is completely deterministic. Given the x's, I just use the formula that I described so far to calculate the values of the neurons at every layer and get the value of the neurons at the output layer, which is some function. But then I add some Gaussian noise. Okay? Now let's compute the MLE for this model. So the likelihood is the probability of observing your data, the observations, y, given the parameters. The parameters here are your connection weights, w, right? And w allows you to compute this f, right? With w, f is determined. But y is equal to f of x plus this epsilon, which is a Gaussian noise, right? So that means that y given w is also Gaussian with mean f of x, which is deterministic, right? And variance I. You can add a sigma squared here. This all becomes sigma squared. You can add some noise. It doesn't matter. You get the same thing. So this probability is just equal to 1 over the Gaussian density, which is like, I don't remember the details, the square root of 2 pi. You have some constant term here. It depends on dimension as well. Right, this is just the Gaussian density. And if I take the log of this, and I'm doing maximum likelihood, so I can do maximum log likelihood. Since log is monotonic, it's the same thing. Some constant plus or minus 1/2. This inverse of the identity matrix is an identity matrix. So I end up with f of x minus y transpose f of x minus y, which is the same thing as the norm. Squared. So maximizing the log likelihood, which is -1/2 f of x minus y, is the same thing as minimizing the squared error in this model where I assume Gaussian noise. And that's true in any model, really. We discussed it in linear regression, right? Doing MLE in a model where you add Gaussian noise from a line. Right, so suppose I want to compute the value of, or draw a point at point x. I draw from a normal distribution. I draw some, with some Gaussian noise, I draw some point, right? And doing MLE in this model is the same thing as doing least squares and finding least squares, best least squares fit to your data with a line. And so this view is kind of, this perspective is kind of nice because it allows you to think of applying some of the probabilistic things that we've used, the tools that we've developed. Like I can do MAP instead of MLE. And as we covered in class, MAP is equivalent to regularization, regularized MLE in a lot of cases. So I can choose to regularize some of the weights to try to help prevent overfitting. I can do like L2 regularization or L1 regularization. L1 regularization will be useful because it could set some of the connection weights to 0, and so I can have it automatically learn which connections are needed and which are not. Yep, and just some closing comments. I just want to say that in general, neural networks are not convex. This objective function is not convex. You can very easily get stuck into local optima, and that was one of the biggest problems of neural networks, and that's one of the reasons why they kind of, fell out of favor and then came back and then fell out of favor again, and now they've come back. So, and the reason why they're popular nowadays and they've, influenced and inspired the whole area of deep learning is because people were able to more intelligently initialize network, have an initial set of weights that are close enough to the global optimum such that running backpropagation will get you quickly to the global optimum itself, right? And some of the techniques for better initializing these networks is like pre-training, which is like training the network greedily, one layer at a time. And also things that have helped are like the improved computational power has allowed people to train much larger networks as well. And another way to make neural networks probabilistic is to actually make each of these nodes random variables. And that's basically creates something called a deep belief network. They're not as popular as neural networks, possibly because they're a bit harder to train. And they're typically, the random variables are typically binary. They're 0 or 1. They don't have to be. And the popular example of a deep belief network, a simple deep belief network, is called the restricted Boltzmann machine. I think we may go further into lecture about that, but I'm not entirely certain. But yeah, so I mean, there's a reason why they're studied. They're really hot, today. In recent developments have really brought neural networks back, and they like in computer vision. They're basically the state of the art for a large number of applications, for most applications, by a fairly comfortable margin. In speech recognition, they're very close to, if not, among the state-of-the-art algorithms. Language modeling, they're not as good as some of the state-of-the-art. They can get, state-of-the-art accuracy, but they take longer to do that. But there are other language modeling algorithms that are much faster, which obtain the same accuracy, that are older. But yeah, there's deep learning has been, getting somewhat of a craze recently. And they're basically just glorified neural networks, honestly. So, any questions on anything I've covered? Okay. Okay, I guess we can stop. Thank you.